Hi, and welcome to Mike Likes Robots, where we share knowledge to accelerate robotics. And today I'm going to have a look at day 15 of Advent of Code. As with the video for day 14, I'm going to try and accomplish it myself for around 40 minutes, in which time I'm hoping to do A and B, or part 1 and part 2. And then if I'm really struggling, I'll stop and either do it myself or find a solution online and then come back, and for the remaining 20 minutes I'll try and talk about what I did and how I solved it. So let's read through this puzzle, and there'll be timestamps if you want to skip ahead. So let's read through. So day 15, Warehouse Woes. You appear back inside your own mini submarine. Each historian drives their mini submarine in a different direction. Maybe the chief has his submarine down here somewhere as well. You look up to see a vast school of lanternfish swimming past you. On closer inspection, they seem quite anxious, so you drive your mini submarine over to see if you can help. Because lanternfish populations grow rapidly, they need a lot of food, and that food needs to be stored somewhere. That's why these lanternfish have built elaborate warehouse complexes operated by robots. I love that there's so many robots in the last few puzzles. I like robots, as you may have been able to tell by the channel name. These lanternfish seem so anxious because they have lost control of the robot that operates one of their most important warehouses. It is currently running amok, pushing around boxes in the warehouse with no regard for lanternfish logistics or lanternfish inventory management strategies. Right now, none of the lanternfish are brave enough to swim up to an unpredictable robot so they could shut it off. However, if you could anticipate the robot's movements, maybe they could find a safe option. The lanternfish already have a map of the warehouse and a list of movements that the robots will attempt to make. The problem is that the movements will sometimes fail as boxes are shifted around, making the actual movements of the robot difficult to predict. For example, and then it gives a list here, or it gives a grid, and then a list of directions. As the robot here it is. This is the robot's position. As the robot attempts to move, if there are any boxes O in the way, the robot will also attempt to push those boxes. However, if this action would cause the robot or a box to move into a wall, nothing moves instead, including the robot. The initial position of these are shown on the map at the top of the document the lanternfish gave you. The rest of the document describes the moves. Hat for up, V for down, less than for left, right greater than for right, that the robot will attempt to make in order. The moves form a single giant sequence. They are broken into multiple lines just to make copy pasting easier. New lines within the move sequence should be ignored. Here is a smaller example to get started. There we go. Where the robot attempt to follow the given sequence of moves, it would push around the boxes as follows, and it gives some examples here. So we're going left first. It can't push the box left because it's already against the wall, so then it tries to go up, and it manages to move up. Then it tries to go up again, and it can't because there's a wall there, so it tries to go right, and it pushes a box to the right. There it is. And then it tries to go right, and it pushes both boxes to the right. Interesting. That's good to know. If it tries to push again, it can't, so it tries to go down, so now it will push all of the boxes down. And then down again, and then left. It can't push down again, so it's against the wall, so it goes left. Down, right, down, left, down, right, down, left. Oh, there's a wall in the middle here. That's interesting. And then the larger example has many more moves. After the robot has finished those moves, the warehouse would look like this. The lanternfish use their custom goods positioning system, GPS for short, to track the locations of the boxes. The GPS coordinate of a box is equal to 100 times its distance from the top edge of the map, plus its distance from the left edge of the map. This process does not stop at wall tiles, measure all the way to the edges of the map. So the box below has a distance of 1 from the top edge of the map, so the wall is included, and 4 from the left edge of the map, resulting in a GPS coordinate of 100 times 1 plus 4 is 104. The lanternfish would like to know the sum of all boxes' GPS coordinates after the robot finishes moving. In the larger example, the sum of all boxes' GPS coordinates is 10,092. In the smaller example, the sum is 2,028. Predict the motion of the robot and boxes in the warehouse. After the robot is finished moving, what is the sum of all boxes' GPS coordinates? Okay, I think this is a fairly straightforward simulation. It gets a bit more complicated when the boxes move along. So we might have to figure out how to code that, but I'll start by pausing here, creating a project. I'm going to include both test cases with tests that check the right answers, and I'll cut to when everything is ready to go. Okay, here we are, and I've created a project for day 15. I've got the test small, I've got the test large, and I've got a main with an empty structure and some tests that check the small against the small value and the large against the large value. So from here, I should be able to start doing the actual parsing. So let's import from string for warehouse. I'm not sure what type of error I'll have yet, so I'm just going to create an enum that does it. Derive debug, enum warehouse error for now. So the type will be warehouse error, function from string. What will my warehouse contain? My warehouse should contain presumably the current structure where the robot is, empty spaces. So let's start defining these. Warehouse cell. It's either going to be a wall or it's going to be an object, I guess. Object. Or it could be a robot. So if I store it as hash map of point against what is contained within it, that should work. So wall, object, or robot. I think I'd prefer the robot to have its own space. So it's either going to be wall or object. That should do it. Okay, let's do that. So this is going to be a hash map that maps a point to a warehouse cell. So it's going to be contents. We'll just call it contents. Will contain a hash map, correct, of point to warehouse cell. Now we don't know what point is, so we're going to go into here and say util equals path equals dot slash util. That should do it. And then we should be able to import a point, and that does that. Great. So next step is that we want to actually start reading things out. We're going to need robot directions. Yes. So we're going to say robot program. Program will be something, a list of directions, I guess. Of directions, and also the robot itself will need a position. Okay, great. So I'm planning to exclude whether it's a wall or not, just to make it a bit simpler to compute. So let's start doing that. So we're going to rename this est puzzle. Let's just return an OK warehouse with an empty structure just to get this working. So it'll be a hash map new, a point will be a 0.00, I guess, and then the robot program will be an empty vector. Now this compiles good, right? So I want to keep a hash map new that I can insert into while I iterate over the puzzle. I also want to keep a this should be none, and we're going to make this an option of a robot. So my first error will be no robot found. Oh, this should be a point, never mind. Okay, so at the end here, if we haven't found, well, I'm not going to bother checking the contents, but I will check the robot. I also want to check that there are some coordinates. So I'm going to have a program. Robot program is equal to vec. So if robot.is none, return error, warehouse error, no robot found, no program found. If robot program dot is empty, I think I can do, yep. Then it will be a no program found. Great. Now we don't care about contents just yet. Actually, we can check, yeah. If contents dot is empty, can we do as empty on a hash map? Probably. No warehouse found for whatever reason. So looking all fine so far. The robot, we should just be able to unwrap it because we've already checked if it's none or not. And then robot program. Okay. These don't need to be mutable. That is true. So now we're going to do the actual reading the code in. So for line in puzzle. Oh, actually, I want to know the width and the height. So the width will be the puzzle.lines.count. Can I not count on lines? Oh, I've done puzzles. There we go. Puzzle.lines.count. Let height is puzzle.lines.first. Can I do a first? No. Can I do an nth? I want the 0th entry. And then I want to let's see, this might be an option. If it's an option, I want to return that there's no warehouse found. Oh, actually, this is not true. Because our puzzle is in two parts, right? We've got this grid and then we've got this. So we want to map by two empty lines. Do we get an empty line? Can I literally just print out what the line is? For line in puzzle.lines. This is me not understanding what we're given, basically. So obviously we'll get errors for this, and then our unwrapped will fail. We can't do a from str on warehouse. I already know how to do a from str. What do you mean? It's here. In puzzle.lines. Oh, let's get rid of that. Actually, don't need that or that. Okay. From str puzzle. I need to use super. Okay, that's better. Now I can also do an impl warehouse function part A, which will take immutable reference to self, although I think that will need to become mutable later. For now, we'll make it immutable. And then terminal, we're going to cargo run. No, cargo test. Obviously, we'll get two failures, but we should be able to see what we get. And it does, in fact, print out the blank line. Okay, so I almost want to just make this naive. I'm going to do let mute grid lines equals puzzle dot lines dot take while l dot is empty. Let, oh, this doesn't need to be mutable actually. Let directions is equal to puzzle.lines.skip. And then I want to skip until the line is not empty. And then I want to take the rest. So I basically want to collect it together, but I should be able to just iterate directly on the directions. Okay, so I'm going to collect this into a vector. It shouldn't be too bad to do that. So my vector will be a vector of and string, apparently. Yep, that seems fine. Oops, excuse me. Now we're going to read out the contents and the robot. So for line in grid lines, we can now get the width and height. So the width will be the grid lines. Actually, interesting. At this point, I can do if grid lines dot is empty, then no program found. No program. That's the wrong enum. That should be no warehouse. Although I'm going to rename that no contents. No contents found. No contents found. And no contents found. Okay, so now I can safely index in at the 0th entry. So this will be gridlines.length. Although we're going to subtract 2 from it. Then we want the height to be gridlines gridlines 0.length, also -2. That's because I'm removing the top wall and the bottom wall, the left wall and the right wall. So that the width will be this much and the height will be that much. There we go. Now, one thing I want to check is that the height is the length. Yeah, so I got that wrong. Be the height there and the width there. Great. Now, I do want to store these into the robot. So we're going to have a width of a U size and a height of a U size. Great. When I do this, I also need to specify the width and the height. Oops. There we go. Now we've got a height, we've got a width for our line. I'm actually going to do some skipping here. So if this would be for row and row index in grid.lines.iter.enumerate. So this is the wrong way around. This should be row index, and this should be a row. Great. So that's the row index. Now I want to do for col index cell in row.iter.enumerate. Firstly, I want to check if row index is if it's 0 or it's height -2, then continue. That's because I want to skip the hash lines. So I'm going to test this by just running again. I'm actually going to comment out the large text because I don't think it's helpful. And what have we got? Yeah, so it actually needs to be -3. Really? That seems wrong. Or have we just missed out? So we've missed out the top line, which is what we want, but we haven't missed out the bottom line. So let's take a -3 on that. That doesn't make sense to me in my head, but maybe it's -1. Nope. Why am I not able to skip correctly? If the row index is 0, or the row index is equal to height -1. Oh, right, because yeah, it's currently skipping out some from the middle. Okay, so we're now I'm just going to print out what these are. I can't believe I'm struggling this much. But so this will be width and height. width. Right. I also want to get rid of this now. 6 and 6. So decimal 0, 1, 2, 3, 4, 5, 6. So I want it to be height plus 1. 2, 3, 4, 6. Yeah. So I want it to be, the length is 6. Is it? It's should be 8 long. 1, 2, 3, 4, 5, 6. That's right. So the height should be 6. So I should skip if it's 7. So if it's equal to height plus 1, then don't print it. Go. There we go. I can't believe that was so difficult for me. Okay, we've got the row. Now we need to do the same thing here. If column index is 0 or width plus 1, great. Now we're going to match on cell. Can we do unrecognized cell as another? And then we can just do an error, and then it will be a warehouse error, unrecognized cell. Okay, so there's a few possibilities. We're allowed this. We're allowed a dot, but we don't do anything. We are allowed an O, because that is an object. And we are allowed the @ symbol to represent the robot. Okay. For this, we are going to... What's wrong with this? Add a match arm. I have. Oh, I need to save. Then it's happy. Okay. In this case, we are going to add... we could just create this outside of the match just in case. Let point is a point, which will contain the column index and the row. Actually, it'll be the... Let's take the column index and the row. We're going to switch to X and Y permanently. So the column index is across and the row is Y. That will be unhappy because it wants I32s from that as I32. And then if it's a wall, then we will insert in our contents.insert. It will be the point, and it will be a warehouse cell. If, however, it's a dot, then we do nothing. If it is an O, then we insert the wall, but it is an object. And finally, if it is the @ symbol, then we set the robot. Robot is equal to some point. Now at this point, we should have our entire grid read out. The next step is to take our robot program and actually read it out. So for... I think the easiest thing here is actually to take our directions string, and I want to take... Can I join it? .collect into a string. Is that allowed? Apparently. Let's print it out and see what it says. Direction string. This only has one line, so I'm just going to separate it out so we can test it. Yeah, that works. Great. Right, so for C in direction string. And it'll be, I'll also have an unrecognized direction here. Great. So I'm actually just going to let robot program is equal to directionstrip.cars.map going to take a C. If I return an error here, I'm just going to do a for loop. It's fine. Directions dot push. Can I do that? No. Directions dot class. Is that allowed? Yeah. Then I can do directions. I don't have directions. I've got robot program, obviously. Robot program dot push. And then we need match C. We're going to push diff C, and then non-exhaustive. Yeah, obviously. We've got our 4 directions. We have got the hat, which will be direction up. We have got our V. I think it's just a lowercase v. I'll have to check that. Yeah, is a direction down. Our greater than will give us a direction right, and our left will give us a direction left. Now this, anything else is just not allowed. We're going to return an error, which will be a warehouse error for an unrecognized direction. That is it. Dir becomes that. We push it, and that's our directions list. Apparently complete. Let's print it out and see what we get. We need to derive debug on the warehouse and the warehouse cell. Cargo test. Test failed. Okay, 4.5 is an object, 4.4 is an object. 0, 1, 2, 3, 4. 0, 1, 2, 3. Point at 4.4 is an object, point at 4.5 is an object. These are 1-based indices. Yeah, that's going to be a little confusing. Let's change those. Try that again. Okay, so at 4.0 we have an object, so that's 0, 1, 2, 3, 4. Yep. At 1.3 we have a wall. 2, 3. Nope. Don't know why you think that. Ah, 1.3 is here. Right. So 0.40 is actually 0, 1, 2, 3, 4, 0. Yeah. 1.3 is 1, 1, 2, 3. Yeah, it's a wall. And then let's check our robot position. It's 0.11. It is. We have our robot program, which is left, up, right, down, left, down, right, down, left. Yeah, that's right. Okay, so I think we're done here. Actually, I'm not sure if I've accidentally overwritten this with something slightly wrong, so I'm just going to recopy it to be sure. I think that's the same, but better to be sure. Okay. So here we are. We've got our grid read in. We actually just need to simulate it now. So I think what I'm going to do is take a mute self. I'm going to implement clone on warehouse, which means my warehouse cell needs to be clonable, and then it's happy. And then my warehouse needs to be mutable. Same thing. Yep. now I can run through all the directions. So for D in self.robot program, I'm going to do move robot and boxes around. Once that is complete, I then need to do some counting. And my counting is it's 100 plus the distance from the top wall, which is 1 in this case. I've got it as 0, but I can quite easily add that on, which means that really I'm just adding 1 and subtracting 1 in various places, but it makes sense in my head. And then add the distance from the left wall, I believe. On the top edge and distance from the left edge, yes. Okay, so let's get a function distance. Function GPS will be, it'll take just a point that is an object. Maybe not. Maybe we can do and self. GPS sum, which will return a usize. And then it'll be self dot contents dot iter dot map dot sum. I think we'll do a filter map, and we'll take an object or a cell, and so it's a point and a cell, but we don't. Yeah, we do. Okay, so if cell is not a warehouse cell object, then return none. Otherwise, we return point.0 plus 1 times 100 plus point.1 plus 1. And it'll be sum of all of that. Filter map. Oh, I need to wrap this in a tuple. There we go. If cell, contents of cell, is not a partial, really? I mean, okay, that's easy enough to do. I'm surprised I need to do it. Partial, I guess it's because of those enum cases where they have some contents inside them. So I can't wrap over a usize. Okay, let's do x GPS is 0 plus 1 times 100. This will be as a usize. Yes, happy? Yes. Let y GPS is point.1 as usize plus 1. Then we're going to return sum of x GPS plus y GPS, also known as sum. Don't need brackets, correct. And there we go. Right. So at this point, we can just do self.gps sum. Done. So now we actually need to do the, excuse me, robot moving around. What's the time at? We're at 30 minutes. I think I'm just going to continue to 40 minutes on this part A. I'm sure it's really important for the puzzle. So I'm going to keep going for now. So for D in the direction, we are going to try to move the robot in that direction. So we are going to say let robot pos candidate equals robot self.robot dot add d dot to point. We ampersand that. Then if let sum cell equals self dot contents.get robot pos candidate. Actually, I guess we can match on it. So self.contents.get. If it is none, then the robot moves. Self.robot equals robot pos candidate. If it is some warehouse cell object, then try to push object. If it is a warehouse cell wall, then we will stop. Actually, that's it, right? We don't need anything. Okay, so if there's a free space, we move into it. No, that's not quite true. We also need to check if it's inbounds. So function inbounds. Inbounds takes an self and a point, or at least a referenced one, and returns a bool. Point.0 is less than, so it's greater than or equal to 0, and point.1 is less than greater than or equal to 0, and point.0, because we're in X, it'll need to be less than or equal to width. No, it'll need to be less than self.width. Width. And point.1 is less than self.height. That's it. Can't compare that because it needs to be as a I32. Yes. And self.height becomes as I32. Undo that, save that, and then our inbounds is done. Right. So if the robot position candidate is out of bounds, if not self.inbounds, robot pos candidate, then continue. That's it. So now our robot position candidate is guaranteed to be within the walls, right? And let's just do that. So, good. Try to push object. So that's our current issue. We can't push the object. So I think there's probably a way of moving an object. Can I move an object? Move point and self maybe, and a reference be an and mute point. A bool. So what I'm going to try and do is let candidate is equal to point.add. Direction will be and direction. Actually, I think that makes more sense to come afterwards. Let's do that. In my head, it does. Okay, so point.add direction to point. Right. Then, if the candidate is not inbounds, then we return false. Return false. Did not move. Cannot move. Not allowed. If, however, it won't be self.robot, it will be, oops, the contents of the point will become the candidate. Oops. So we need to do this will be false. An object, it depends. And for this one, true. Okay, so if there's an empty space, we move into it. Otherwise, this needs to be something, which we need to do. So if there is an object there, then we will let mute inner point is equal to self.contents.get mute. And it will be the candidate point. Candidate point. If not, if self.move point will be inner point, direction will be my direction, then we move and return true. Else, return false. Okay, this needs to be, oh, it's an option. I know it's not because I've already checked. I know there's something there. I mean, I can just get mute here. If I get mute and candidate, maybe I can do let inner equals self.get mute. I think I'm just getting confused here. So I think I want next point, next obj will be, can I get an entry? Entry mute point and candidate. Match next obj. If it's okay, then we go to next point. Okay, what's wrong with this? So entry for a key, it returns an entry. I guess I can't do that. Occupied and vacant are not covered. All right, forget that. I feel like there's a way to do it, but I can't. So I don't actually want to get mute. I want to update the key. That's the thing. So let's do a hash map get mute, get key mutable. I think this is an issue. So I think what I'm trying to do is modify a key in place, which doesn't make sense because it's a hash map, right? So I think what I need to do is I need to say whether it can move there. And if it can move there, that's when I do the move. So for a given candidate point, if it's able to move, if there's nothing there, return true, right? So this doesn't this just becomes a point and a direction. However, we've got our candidate point, right? Then if self dot, it would be move point still, then it will be and inner point. But it's our candidate. It's our candidate point. If self.move point in the direction, then we remove self.contents.remove entry candidate. Wait, if I do remove, do I get something? Yes, I do. So at this point, it will be let obj is equal to self.contents.remove, and then self.contents.insert. It will be the candidate point, candidate, and the object that I just read out. Great. This needs to be .unwrap because I have just checked if it exists. And it certainly exists due to match loop, match clause. Right, and then return true. Otherwise, return false. Okay, self.contents, we can't do that because that borrows mutably. Done. So now we are allowed to do this, apparently. If I can move the point, then move the point. Right, so now I can get the robot position candidate if it's not in bounds. So I do have this logic twice, which I'm not sure I need. So self.robot becomes robot position candidate. Otherwise, we move the object. Self.move point, and it will be the robot position candidate. If self.move point, then self.robot equals robot pos candidate. Done. Move point requires a direction as well. Yep, D. Can't do that because it's also borrowed as immutable. Where is it borrowed as immutable? Borrow occurs here. Okay, I'm going to run this so that I can see the output. Mutable borrow occurs here. Yep. Immutable borrow occurs in the iteration. Okay. I'm just going to copy that then. So let robot program equal to self.robotprogram.iter. Not iter, clone. Can I just clone it? Yes, and that gets rid of it. Okay, test failed because of a bigger number. Well, that is honestly promising. That meant that we ran through the directions. So let's I think it would be interesting to print it out at this point, but I am over time, so I'm going to cut here and continue on to the point where I have a working simulation.
Okay, so I'm back and I figured out what was going wrong. The basic reason that it was going wrong was because, well, there were two reasons. The first was that using the point class, but swapping whether they were 0.0 or 0.1, did throw a bit of a spanner in the works. And that's because when I have a direction and it has a 2-point method, it is assuming that the row is the major and the column is the minor. whereas I tried to do it as X and Y, and that was different from row major, column minor. So that was the first thing. I changed it over to have that. And then the other thing was that for the logic to push objects around, it was using the same point. So if I said, try and move the candidate location, and if it's possible, then move the object into that location. But the trouble is, I'm moving the current object into that location and the next object into the same location. So I was overwriting the object, or rather putting them in the same position. It meant that objects would overlap and the robot would overlap with objects too. So what I did to fix that was to add direction to point, so it adds it on again to the candidate because it's all going in the same direction, so that's fine. After that, it started to work, at least for the test. I haven't run it for the full input yet. Zoom in a bit on that. To figure out that this was happening, I made a print grid function, which basically just reprints the walls and the @ symbol for the robot, hashes for walls, and O for object. And by doing that, if I make the test fail, I could see for each direction that it was moving. So we started with a warehouse. This is the initial state. We moved left, we moved up, we moved right and pushed an object with it. We moved right and pushed both objects over. We moved right again and both objects hit the wall, so they stopped. So you can see that this logic is now working. So what I'll do now is I'll take out all the print statements. Actually, no, I'll take out all the print statements. Right, so anytime it says print grid, we are going to, I'll get rid of that. That should remove everything. I'll just put up with that warning about dead code for now, I think. Okay, run the test again. Test results are okay. So now I'm going to put the full input in. So let's get the puzzle input, much bigger grid, many more directions. And we're going to create the input.txt, paste it in here. That looks right as far as I can tell. And then we're actually going to create the main function. It's so funny that it takes so long to make the main function when you're using unit tests to verify everything. Okay, main function, here we go. We're going to have a let puzzle equals include string from puzzle input.txt. Then we're going to create our warehouse. Warehouse from string puzzle dot expect could not parse puzzle warehouse. Print line part A warehouse dot part A. And this is mutable. Yes. I wonder if I can declare this as immutable and then clone it for part A, because I don't want it to affect part B. Yes, I can, because I derived clone earlier. So now part A is taking a copy of the warehouse and then finding the part A result. Okay, let's run it. Cargo run. And there's still a lot of print statements in there. Let's get rid of that. And the hello world. That's fine. Okay, let's run it again. And there we go. Let's check whether it's the correct result. And it is. Excellent. So let's go on to part 2. Part 2. Let's have a read through. Looks like we've got some new objects to worry about. The lanternfish use your information to find a safe moment to swim in and turn off the malfunctioning robot. Just as they start preparing a festival in your honor, reports start coming in that a second warehouse's robot is also malfunctioning. The warehouse's layout is surprisingly similar to the one you just helped. There is one key difference. Everything except the robot is twice as wide. The robot's list of movements doesn't change. To get the wider warehouse's map, start with your original map and for each tile make the following changes. If the tile is hash, the new map contains hash hash instead. If the tile is O, the new map contains double bracket instead, left and right. If the tile is dot, it now contains dot dot. If the tile is at, it now contains at dot. This will produce a new warehouse map which is twice as wide and with wide boxes that are represented by left and right square brackets. The robot does not change size. The example from before would now look like this. I see. Because boxes are now twice as wide, but the robot is still the same size and speed, boxes can be aligned such that they directly push two other boxes at once. For example, consider this situation. Left, down, down. After appropriately resizing this map, the robot will push around these boxes as follows. It pushes the two left. It moves down. It moves down again. It moves left. It moves left. It moves up. And now this box, which is connected together, will push these two boxes. Okay, that is trickier. The warehouse also uses GPS to locate the boxes. For these large boxes, distances are measured from the edge of the map to the closest edge of the box in question. So the box shown below has a distance of 1 from the top edge of the map. Hang on. Doesn't oh, I see. Oh, that's annoying. It's because the walls along the side are too wide, but along the top are 1 thick. So the box shown below has a distance of 1 from the top edge of the map and 5 from the left edge of the map, resulting in a GPS coordinate of 100 times 1 plus 5 is 105. In the scaled up version of the larger example from above, after the robot has finished all its moves, the warehouse would now look like this. The sum of these boxes' GPS coordinates is 9021. Predict the motion of the robot and boxes in this new scaled up warehouse. What is the sum of all boxes' final GPS coordinates? Okay, I don't think there's anything too drastically different in what we've written. It's more of an extension. So let's go ahead and write it. I don't know if I think it will be easier to copy the warehouse and change it, or to change what is currently there. I think it's different enough with GPS and the movement logic and what can appear in the puzzle that I will copy it. So I'm going to create a warehouse.rs. We're already getting pretty cluttered here. Here I'm going to copy the entire warehouse impl. And here it will be a pubstruct warehouse with from struct will be pub and pub function part A. There we go. Now I can delete this. And I can declare my modules. So my module will be module warehouse. And I will use warehouse. Okay, now I need to get some imports going for this. So we'll need a hash map, we'll need a point, and we'll need a direction. Is that it? From struct. type error is warehouse error. It can't leak a private type. So this does need to be a pub. And print grid is unused. That's fine. So now we can get rid of that. And it's mod warehouse. And there it is. That's it. So now we don't actually need to clone this part A. We can just directly make this mutable. And then we can create a new file, warehouse wide.rs. I'm going to copy the contents here in. Actually, I'm going to call it wide warehouse. And within wide warehouse, it's the same error. So in fact, I should probably put that into its own file. Let's do that. Warehouse error. And then in main, we can use a mod warehouse error. Oops. Excuse me. There we go. Great. Let's take this updated. Oops. I copied it into the wrong file. Updated thing into here. Create warehouse error. Great. And now we're actually going to have a left object and a right object. Okay. Let's get rid of this line. Let's also actually compile it. Mod wide warehouse. And then we're going to use wide warehouse wide. Oh, is it still called warehouse? Yeah, it is. Import from string and import. Presumably I create it somewhere in fromstr and also need to change the name there. I could just call this self and then I don't ever need to update the name. There we go. We're back in main.rs. We need a semicolon. That doesn't exist, so we rename it wide warehouse. And now we can do let mut wide warehouse equals wide warehouse double colon fromstr puzzle dot expect could not parse wide warehouse. Okay, and then we're going to create part B. And in here, this is not a wide cell, this is a warehouse cell. This needs to be updated, so I'll get to that. It's the part A function that I want to rename to part B. Here we go. We actually need to update this to the new logic. Print grid. I'm just going to get rid of this because I can copy it in from part 1 and I still need to update it. So we've got some things to update for this. First, we're going to start with this logic. Now, the width is going to be twice as wide. So that's the first thing. Good. Actually, I will keep the print grid function. I'm going to print it immediately after constructing it so that we can see that it's doing the right thing. Okay. This is so far right. We'll change this to left object, which will be a left angle bracket, and a right object, which will be a right angle bracket. If we see a wall, it will still be a hash. Otherwise, it's a dot, and the robot takes 1 space. Yeah, this is all fine.
Good. We need to update this GPS sum. We need to update this move point. We need to update this part B. And I think that's it. Here we go. So let's take this logic. We're gonna call this left point, and we're gonna call this right point. Now, the first thing is that the column index is getting doubled, right? Column index -1 times 2. There we go. And we're going to do the same thing here, except this will be column index -1 times 2 plus 1. I think that's right. So for this, we're going to insert on left and right. For this, we're going to insert left and right, but this will be the left object and this will be the right object. And then for the at, it will be the left point. Okay, that's from str complete. Now we're going to put a test in. I don't need this. I would like this, which prints it out for me. And then I want to assert false. Okay, let's run this test. Part B in main.rs. We're just going to remove this for now. Code test. Okay, we've got test failed and we want to print grid, not the whole thing. So let's do that. We want to warehouse.print grid. Run that. Okay, what do we got? Something that looks pretty similar, I have to say. Let's take the consider this situation. Do we get the answers for this in the scaled up version of the larger example from above? Okay, so I don't think this is right. Test small is, yeah, it's got different boxes. Let's do a test small wide.txt because I would like it to look the same. Oops. Keep that. And then in wide warehouse, we're going to take test small and wide. And then we're expecting its initial state to be like this. So let's run this again and we get, it's not quite the same because we need to put in 2 hashes for the walls. Otherwise it looks the same. So it's actually fine that I can do that. Let's take our print grid code. We just hash instead. And then hash, and then hash. That should do it. Nope. Because our grid is already the right size. So for the top and bottom, we don't need to do it. For the walls, we do. So where am I? Print grid. No, here, print grid. I would like this to be a single hash, and I would like this to be a single hash. Now we run it again and we get something that again isn't quite right. There we go. Test small wide produces this. And that looks right to me. Yeah, everything's good there. Okay, so with that, we can remove this for now. Within bounds, it should be fine because we still got width and height. So let's figure out our new pub function, part B. Gonna take this and uncomment it. Now, because we don't have a GPS sum, I'm just going to return 0. So our robot program, is there anything that we need to do about this? If it's left object or it's right object, then move point, which of course doesn't exist yet. That should be fine. This is actually, we can rename this move object. I named it move point because I thought it might be used for the robot, but actually I'm only using it for walls, for objects rather. So I think for that reason, I'm happy enough to just make it a move object function, and the same in here. Move point, all of these should be renamed to move object, but without caps lock on. Move object, there we go. Okay. So now we're going to take the left object, and how we act is different based on whether we're moving in the left direction or the right direction. So given that I've already spent quite a bit of time on part A, and we're now up to about, well, I've now spent a fair amount of time on part B. I'm going to try and code some of this stuff and get it working and show you the finished result at the end. Try and keep the videos a slightly more manageable length. So for that reason, I'm going to do some coding, and I will come back when I'm done. Okay, here we are with the test at least passing. I haven't run it on the full system, but there's been quite a lot of changes. So firstly, I was implementing a new GPS, which I had misunderstood. So instead of it being from the edge of the box to the closest edge of the map, it's still from the left and the top, just to the closest edge of the box. So either the left or the right, whichever is closest, which made it a lot simpler than I was making it. So for a while, I was just struggling with that. Otherwise, I have modified how the simulation runs. The simulation now, instead of having the logic duplicated once in the actual part B function call and once within the move object function call, it's now all done within one function call. And I do that by also creating a warehouse cell robot and inserting that into the map. So now the structure contains the robot position as well as the hash map that has robot as a cell type. So by doing that, I can use one function to get the moves and then implement them. So we've got the move robot and boxes function. And what this will do is figure out which moves to make. Now, this is another point that's different. Before, I was just making the moves and it went from the end to the start, but it doesn't work as well in this case because where the left of a box might be able to move, the right of the box might be obstructed. So we can't just move everything on the left and then go, oh no, the right didn't move. We have to backtrack. Instead, I've got a move stack which builds up a vector of old point to new point. And that's done by recursively calling and checking whether it can be moved. So there's quite a big match statement here, which checks all the possibilities exhaustively. So first it checks what is at the point that is trying to be moved in the direction, and it also checks where it's going. So for example, if we're a robot and we're moving into empty space, that's fine. We return a vector saying, yep, that's fine, move from old point to new point. If it's a robot going to a left or a right object, then we can create the move from the robot to the new point, and then check whether the left object and the right object can be moved. Either one, left or right, because then it will recursively call into build move stack. So at the end of this, because it's possible that it can move or it can't move, what we actually build up is not a vector of point to point, it's a vector of result of point to point, where it can also be an error. And by doing that, we get a stack that we can check is completely valid before doing any moves, which is what is happening here. So what happens is we build the move stack from the current robot position in the direction. We also keep a hash set of places we visited so that the left object doesn't check the right object, and then the recursive function call has the right object checking the left object. I had Stack Overflow from that. By keeping a visited hash set, we can check whether it's been visited already and then not do it. And then once we've got the move stack, we collect it together into a result of vectors. A result where the OK is a vector type. So that's a Rust thing. You can move inner results to one outer result and then check it. So by doing this, it becomes, instead of a vector of OKs and errors, it becomes one OK containing a vector or an error. So I can check that error with the question mark. So now here, my moves is a vector of point to point. The first thing is that the moves will always have the robot move first, in which case I move the robot. However, if the move set is empty, then I return an error that it's an unexpectedly empty move list. And then I had another problem, which is that when I first did this, I iterated over the list and moved the old point to the new point. But I had an issue, which was, yes, this map demonstrates it. When I tried to move this box, it then checked these boxes, and this box could move up. So what should have happened is that this should become ... This should become left, right. But instead, I was getting some variation of a part being overwritten. And that's purely because of the order of the moves. I moved this to here, and then I moved this to here, and then I moved this to here. And then I moved this to here so that this was a right angle bracket, and then I moved this to here and made it an empty space. And so by doing that, I was doing the same, I was overwriting moved parts. So I changed it to, instead of doing one iteration, it now does 2 iterations into a cloned version of the map. So we clone the version, we remove all the old positions so that it's a duplicate of the map except for all the points that are being moved. And then it gets the old points from the old map and inserts them into the new map. So that's how I can stop overwriting my own points. So it's quite a lot to work out. It took me really a long time to figure all this out, but I did have a lot of fun doing it. There's another part actually which is worth mentioning, which is that to figure out this test small single, I built another function to read in the map, which is alt from string, which essentially just does the same reading in logic as the original warehouse from string, so that I can pass it in a full map instead of one like this with O's in it. So by doing that, I could run test cases on stuff that had been partially simulated, for example, which really helped me figure out what wasn't moving. With that, I think that's everything to go over in here. Now that I've shown you the alt from string and I don't need it anymore, I'm going to delete it. I also technically don't need the print grid, but I am going to keep it because it's different, so it might be interesting to look at. And so from there, I'm going to go into, I don't know why this has changed, so I'm just going to save it and hope I didn't break anything. And go into main. So from here, oh, that's a test. We want to be able to run the part B. And we can't because there's no method found. That's pretty weird. We're calling it on warehouse, not wide warehouse. There we go. So at this point, This is my first full run, and I don't know if it's going to work. And it did something. And it is the right answer. So that's it. Day 15 is complete. With that, next video, I'll be moving on to day 16. Thank you for watching, and I'll see you in the next one.